Thanks everyone for coming in for String Theory seminar series. Today we have Robin Schneider from Uppsala University, and Robin will tell us about deep learning Calabi-Yau metrics. Thank you.
Thank you. Thanks for giving me the opportunity here to speak. So thanks for the organizers. And yeah, as said before, I'm going to tell you today about some recent developments which are not on the archive yet, but which will hopefully appear soon on the archive about deep learning Calabi-Yau metrics. So I guess this is a very hot topic. There have been some 4 papers or 5 papers over the past half a year coming out, and I hope I can convince many people of you today that this is worth something to investigate, and it's a very interesting topic. In particular, I will present to you today a new package for deep learning Calabi-Yau metrics, which will allow you to find numerical approximations to these metrics within maybe 20 lines of code. So this is work done with Magdalena Lavros, Andre Lucas, and Fabian Röder, and yeah, it will appear soon in the archive. And yeah, let's begin. The outline of this talk is as follows. First, I'm going to motivate a little bit why are we interested in Calabi-Yau manifolds, and why are we in particular interested in Calabi-Yau metrics. Then I will present this new computational package, which is called CY-metric, and we'll show you a little bit how to learn Calabi-Yau metrics with it. And finally, I will show 2 experiments, one on the Fermat Quintic, which is everyone's favorite toy model, and one on the Bicubic, which is interesting because it admits to Kähler moduli, and our package is able to learn the metric at particular points in Kähler moduli space. Okay, let's begin. So why are we interested in Calabi-Yau manifolds? Well, if we come from string theory, be it the heterotic string, be it F theory, we usually connect or try to connect with the observable physics by compactifying 6 or 8 of these additional dimensions. And this is usually done on a Calabi-Yau manifolds. And Calabi-Yau manifolds are very interesting manifolds. We do know a lot of things about them, but most of the things we know about them are their topological quantities, so they're global quantities. We do not have any closed form expressions for the metric tensor in Calabi-Yau 3-folds or higher. The metric tensor itself, however, is very important in order to connect string theory with observable physics. So if we want to compute the physical Yukawa couplings, we will need this metric tensor. There has been some recent development which you have heard about by Mosen and Matt in this string seminar series, where we can make topological statements about the Yukawa couplings. But in principle, to make real connection with the low energy physics, we will need the metric tensor. It is also interesting for the whole Swampland program. For example, Ashmore and Röder at the beginning of this year published a paper where they were investigating the Swampland distance projector with numerical approximations for these Calabi-Yau metrics. And finally, for the more mathematically inclined people here, the metric tensor is also interesting because with it we can test, for example, the SYZ conjecture. Okay. Now that I've motivated this, we'll have to talk a little bit about how can we find this metric tensor, because there are no analytic expressions for it. So the first approximations for the metric tensor relied on the so-called Donaldson algorithm, which was published by Donaldson in 2005. And this one has been used by various research groups over the years to find approximations for the metric tensor on selected toy examples, mostly the Fermat Quintic, but also other Calabi-Yaus with high degrees of symmetry. The problem with the Donaldson algorithm is it does not learn the metric directly, but it learns it's an iterative procedure to learn the Kähler potential. And this is rather expensive because in order to get the metric from the Kähler potential, we have to take 2 derivatives, and this whole procedure scales really badly in terms of accuracy and sample efficiency. So more efficient proposals are based on energy functionals, which also approximate the Kähler potential, but find a better basis for it. This has been made popular by Hedrick and Hassar, and there's also some recent developments by Quinn and Gray. And over the last year, I would say, maybe a bit earlier, different research groups started applying methods and algorithms from machine learning to learn the metric. There are different approaches for this. So some of them try to learn better approximations for the scalar potential, and then in particular, the research groups around Anderson and Chijada were learning the metric directly. And this talk today is also going to be in line with the proposal from these two research groups to learn the metric tensor directly. Okay, so let's briefly review a few facts about Calabi-Yau manifolds. First, on any Calabi-Yau manifold is a complex, compact Kähler manifold with vanishing first Chern class. And on any of these manifolds, we have two nowhere vanishing differential forms. There's a two-form J, a real two-form J, which has an associated metric G. And then we can also define the holomorphic n form omega. So we do know, however, that this J is not unique. Given any J prime, there exists in the same cohomology a unique representative of this J with the metric G, and this metric G needs to have vanishing Regge curvature. So we can combine these two nowhere vanishing differential forms into a second order Monge-Ampere equation. We know that, say we are studying a Calabi-Yau threefold, we know that H33 of this Calabi-Yau manifold is equal to 1. So if we construct the top form, either by wedging J 3 times or by wedging omega with omega bar, we get something unique up to some constant number. And this is very interesting because this allows us to efficiently approximate the Calabi-Yau metric without relying on computing these derivatives from the Kähler potential and then again computing the derivatives to find the Ricci scalar directly. So yeah, the results of this talk today is essentially a Tensorflow library, which you can find online. It's on GitHub. This is currently a very bare bone alpha version, and I will post the link later on again, so for people who want to see. And this package is called Cerametric and includes essentially two modules. The first one is to generate points to train our neural networks. And the second one are different TensorFlow models where the user can specify the complex modulize and the Kähler modulize, and then after some training, the module is going to give you some Calabi-Yau metric on that manifold. Okay, so how are these metrics being done? In general, the metric on the Calabi-Yau threefold is going to be some 3 by 3 Hermitian matrix. So the easiest thing is like we can treat the neural network as some kind of black box, and it's going to predict us 9 real numbers, and then we can take these 9 real numbers, put them in the 3 by 3 Hermitian matrix, and we're going to have a prediction. However, we've seen before already that there's some physical intuition which we can use, and that is for some already known metric, Kähler metric on this manifold, we can just add a correction. And then at some point we will have to arrive at the exact metric if this Monge-Ampere equation here is satisfied. So we have different answers which we test and which I'll show you later in the talk for this physical intuition to improve the performance of our neural networks. And in particular, I want to emphasize this phi model here at the bottom, which is where we take the Fubini study metric, which is known, which we can compute analytically, and then we add an exact correction to it of this Monge-Ampere type, and we'll see the performance. This has the advantage that this metric is already going to be Kähler, and also in the same Kähler class as the Fubini study metric. So having defined these neural networks here, we will need to specify some training data. And training data for these neural networks are, of course, the points which we sample randomly from the manifold. This procedure is unfortunately not very trivial because depending on the way we sample these points, we might introduce a bias in our data set. So in order to get an unbiased data set, what we could, for example, do is like we sample random points in our ambient space and then discard all the points which are not lying on the Calabi-Yau. This is unfortunately very inefficient because of the high dimensionality of our problem, and the Calabi-Yau is just going to be a submanifold in this high ambient space. Thus, we will have to reject essentially all of the points, and we'll never really find any points on the Calabi-Yau. The other procedure is to give random values to all the coordinates and then solve for the last one. This, however, introduces a bias which is more difficult to control. what we can do is we can employ a theorem by Schiffman and Zeldich, which then has been generalized later on by Brown and others to products of complex projective spaces. And this theorem is a bit more involved, and I don't think I will have the whole time to go through all the details of it, but I'll try to sketch it a little bit. So what you do is you have a Calabi-Yau defined by n hypersurfaces, and then you distribute 3 parameters and construct lines and subsurfaces in the different projective spaces, which make up the ambient space. And you construct them in such a way that you have a known ambient space measure from the construction. So you sample random points on these ambient on these projective spaces, on these ambient spheres, and you sample 3 points, for example, and then you construct a surface. We can then take the intersection of these surfaces with the defining Calabi-Yau equations, and then we know that the solutions to this intersection are distributed with respect to some non-ambient measure, dA, which if we take only points on the sphere corresponding to each complex projective space, this is essentially just the pullback of some Fubini studio metric again. And this allows us to integrate any quantity via Monte Carlo integration over the manifold. So we have some quantity f, and then we integrate it over the manifold by introducing these integration rates, which are given by some antisymmetric product of pullbacks of some ambient measure. This equation here is important because the benchmark how to find or figure out if we have a good approximation to the metric tensor rely heavily on this Monte Carlo integral. So in the literature, there are 2 benchmarks which are called the sigma measure and the Ricci measure, and those are essentially these quantities f here integrated over these Monte Carlo integrals. Okay, so neural networks, we've treated them so far as a black box, and I don't think it's useful to introduce them here. But the way they are optimized is you have some cost function, which the neural network minimizes and finds parameters in its weights such that this loss function is going to be 0. And often in deep learning, you do supervised machine learning, where you have some true value, and then you just take a difference and want to optimize the prediction of your neural network in such a way that this difference is going to go to 0. However, we don't know any known expression for the metric tensor. So what we do instead is we have the metric tensor has some properties, and we enforce these properties in the loss function. So that gives us a long custom loss function with different contributions, and those are, on the one hand, the Monchampere equation, essentially, which we had before. On the other hand, we want our metric to be Kähler. So we take some partial derivatives here, and then we flip some indices, and we want that every entry of these tensors is going to vanish. Then we want it to be well defined over all patches. Say we compute the metric in one patch, we go to a different patch, and then we can define these patch transition matrices, and it should be 0, the difference between those 2 things. We can also learn directly against the Ricci scalar, which we disable in our package by default, because we know that if and only if the Monchampere equation is satisfied and the metric is scalar, this should automatically vanish. And finally, we introduce an overall volume loss, which forces the metric to be at the same overall volume as the Fubini studio metric for which we generate the point. Good. So let's start with an example. We consider the Fermat Quintic, which I think most people of you will know, have seen before in your life, which is just a homogeneous degree 5 polynomial in P4. And this Fermat Quintic we can also set up with the package. So I'm going to have about 20 lines of code here. I hope people are probably not going to be super familiar with Python, but Python usually reads very much like pseudocode. And I'll briefly go through these lines and explain what we're going to do here. So we first import some library which lets us manipulate any kind of tensors or matrices, which is called NumPy. And then we import the point generator from the C-metric package. In the next 4 lines, we essentially specify our Calabi-Yau manifold. So we have the basis of monomials, which are dzi to the power of 5, which you specify here. We have the complex moduli, which are all going to be 1, which is the one sitting in front of these monomials here. we have the volume moduli, which is just going to be a single one because we're working in a P4 ambient space. And then we define also the dimension of the ambient space, which is dimension 4. So we can initialize the point generator with all this information, which describes our Calabi-Yau manifold, and then prepare a training data set of, say, 200,000 points. On top of that, we have to prepare all this information for our neural network to work with, and this is just called prepare basis here. So on the next slide, we're going to learn or teach the neural network how to find a metric tensor. And this is going to be a bit more complicated, but I hope we get through this. So again, in the beginning, we just import some packages. We're going to use Tensorflow. Tensorflow is the backend which does all the neural network computations for this package. We will learn a particular model of the 5 models you've seen earlier on the slides, and this is the element-wise multiplication model, which has also been used by Anderson and others last year. Then we load the training data and we load all the information of our Calabi-Yau and save that in these 2 variables. We compute the kappa value in the Monch-Ampere equation, which we had above before, from the integration rates. So this is a known formula. And then we set up the neural network. And the neural network is going to take 10 input parameters because we have 5 complex coordinates in the ambient space from the P4. But since neural networks work usually with real numbers, we will have to multiply that by 2. And we take some number of hidden layers with some activation function. And in the end, we're going to predict these 9 output real scalars. Yeah, we can set this up together and initialize our element-wise multiplication model. And in the next step, we want to train the whole model. So we define some custom metrics which TensorFlow keeps track of during the training, so we can make some nice plots afterwards. Compile the model with an Adam optimizer, which is going to do the training for us, and finally train. And then it's done. Now you wait a little bit, like 100 epochs, which is on a modern laptop probably going to take you 2 hours, and you get a metric from the Calabi-Yau. And I hope, in these plots, I can convince you that we indeed find a good metric. So there's going to be a lot of plots. I'm not going to have the time to go through all of them. But the first thing I want to emphasize is what we can see here is we have the 5 different models, which I proposed before. We have the multiplication models and the prime model, the free model, and addition correction. We now plot here the different loss terms which we found on earlier slides. And what's very important here is to see that we do not overfit between training and validation data. I mean, this one is oscillating a little bit more. That's always going to be the case. It's not going to be as smooth as on the training data, but the values are approximately going to be the same, as you can see here, around 10 to the power -1. In similar fashion, we can see that the transition loss is going down for all these models, and also the validation loss, in particular for the 3 working models on the Kähler constraint, is also going down. The phi model here, you won't be able to see here because it's by construction Kähler, so it's going to be somewhere 10 to the power of -7 at the bottom, and then you can't see any of the other results. More importantly, there are these 2 benchmarks from the literature where the Donaldson algorithm is usually being evaluated against, and those are called the sigma measure and the Ritchie measure. And with our package, we can keep track of both of them during the training process on some separate test set, which the neural network has not seen before. So we can see that both of them get optimized very well. And this is a rather non-trivial check of this Monch-Ampere equation. And I don't think it has been studied before in the literature to see that the Ritchie measure also decreases with an actual decrease in the sigma measure. I mean, this is something we would expect because if this one is going to be 0, this one has to be 0 too, but it has not been studied before. So maybe nice to notice here is like this is a value of 10 to the power of -2, which would correspond to Donaldson algorithm with k equal to 20, which takes about 35 years on a laptop, while the neural network takes 2 hours of training. And then on the last part, we plot this relation between optimization of the surrogate loss function, optimizing this Monge-Ampere equation, and actually the decrease in Ritchie measure. And we find some nice linear relationships for almost all of these models, which go neatly through the Ritchie measure. So here's a relationship between sigma measure and Ritchie measure of roughly 0.06 is the slope here.
Robert, you got 5 more minutes.
I've got 5 minutes. Okay, we can do this. 5 more slides. Okay, the second example I'm gonna tell you about is the bicubic manifold, and this is a degree 3 polynomial in P2 times P2. And here we pick a member of this family which is invariant on a Z3 symmetry, and this has 2 reasons. First of all, we usually want some Calabi-Yau with 3D acting symmetries and heterotic compactifications. And second of all, it simplifies the problem a little bit. So this is 34 monomial terms here. And if I would just pick a generic member of this family, this polynomial would have 100 terms. Okay, good. I'm going to show you some more fancy plots. In similar fashion to before, what we can see is that the loss is decreasing nicely for the element-wise multiplication, the matrix multiplication, and the phi model. We see that we are not overfitting to the data. We see that we are staying roughly at the overall Calabi-Yau volume, and we find this linear relationship. The important thing, though, for the bicubic is this overall volume only takes a linear combination of the Kähler moduli. So this does not actually tell us that we're going to stay at the same points in Kähler moduli space. However, we can check that this is actually the case by computing a quantity, which is the slope of some vector bundle. And this quantity is a topological quantity, which I think we have also encountered in this lecture series by Sebastian 2 weeks ago. And we can either compute it by integrating the first Cherenkov, or we can compute it numerically via some Monte Carlo integral again. So in the table below, we computed this quantity, and we have some true values, which are going to be 0, 0, 18, 45 for some selected line bundles. And then we can, first of all, check how our point sampling works. So in order to have points which are representative globally over the whole manifold, if we just compute this quantity with respect to the Fubini-Studi metric, we should match the true values, and this works fairly nicely. And then we can also compute the slope again with the Ritchie-Flat metric, taken now from the phi model because it was the best performing model in the plots before, as we can see here, as the lowest Ritchie, as the lowest sigma measure. And again, within one standard deviation, which is computed from the average of these 5 experimental runs for the phi model before, we can see that the true value is more or less getting matched. Okay, good. Finally, okay, coming to the conclusion and outlook, I presented to you today a new package, machine learning library, Metric, which translates the problem of finding Calabi-Yau metrics to a rather straightforward machine learning task. I think our package is the first package which allows for the computation of this linear relationship between the surrogate loss function, Monge-Ampere loss, which has been used in the literature before, and actually the vanishing of the Ritchie scalar. Furthermore, I presented to you a model which allows for learning the metric at particular points which are specified by the user in complex and Kähler moduli space, which is nice. And finally, the TensorFlow models in principle work for all complete intersection Calabi-Yau manifolds, but also for the toric Calabi-Yau manifolds. So there's a much larger class. There are currently some hiccups which need to be worked out for the point generation, but the TensorFlow models work fine for the Calabi-Yau manifolds also coming from the Quetzalcoatl list. In the future, a few things that need to be done. So first of all, we will need to do some more hyperparameter studies find good experimental setups, good experimental configurations, which generalize well over different kind of manifolds. We want to learn a bundle metric, of course, to make some more progress with the U-cover couplings. What can be done else is we can compare our results here to the exact solutions which are known for pair 3 manifolds by Kähler and others. This would be very interesting. And finally, we welcome contributions. So if anyone has additional ideas, functions they want to be implemented, yeah, just drop us a message. Okay, I think that's it from me. 5 more minutes.
Let's thank Robin for his excellent talk. And Craig, do you have a question?
Hi, yes. Thank you for this nice talk. So I was curious about how much more difficult the machine learning problem gets when you increase the Hodge numbers. So I'm thinking of something like H31 being about 300,000.
H31, you mean a Calabi-Yau 4-folds now?
Yes, 4 folds.
Okay, we haven't studied Calabi-Yau 4-folds yet. In principle, the package works, but I cannot tell you. I mean, this is a very large number.
Okay, but
so
even
from,
in the threefold context, do you see some difference in like time to train or so on in these cases?
I mean, definitely, yes. Yes, we do see. I mean, there's a reason why we picked here still very simple examples. In principle, this whole thing works for larger Hodge numbers too. But you can already see if you, so when you had the Bicubic here, I lowered the number of complex coefficients which are non-zero here from 100 to 34 because it takes a little bit more time if I take all the coefficients. In similar fashion, if you're going to take a Calabi-Yau manifold with a very large H11 value, I think it's not going to be possible yet due to some optimization which needs to be done. I mean, I think if you have like 1,000, I don't think this is possible.
Okay.
But it's the first step in the direction. I haven't tested it, but yeah, there's definitely a decrease in performance.
Very good. Thank you.
All right. Is there any other question? Okay, then let's thank Robin again